Hello guys, welcome back to another video on my channel. So in the last video we did a double integral. In this video I want to start a series of UK integration B round 1 problems. There were 30 of them and I will aim to make 3 parts, 10 videos in the first part and the remaining in the remaining 2 parts, evenly spaced. So let's get started. Question 1 was integral with this weird dash sign, which I will explain, -1 to 1, e to the in dn, where integral dash, which almost looks like an f, from a to b of f of x equals 1 over b minus a integral, regular integral a to b, f of x dx. So it's more like an average integral. Okay, so we can write this using the definition as 1/2, because we have 1 over 1 minus of -1, which gives us a total of 2, -1 to 1, e to the in dn. This is a very easy exponential integral. That's just e to the I n over 2 I from reversing the chain rule from -1 to 1. So in the end we just have e to the I minus e to the minus I over 2I, which, if you recall the definition of the sine function, is just the sine of 1. That's it. That's how you solve it. There's nothing more to it. Now question 2 was integral 1 plus 2024 x to the 2024 e to the x to the 2024 dx. Now the way to solve this is to split this up so that we have the first integral with the 1 times the exponential e to the x to the 2024 dx plus integral 2024 x to the 2024 e to the x to the 2024 dx. And if you have sufficient mastery over derivatives, you will realize that if we by parts the first part, so if we do by parts on this integral, so when we do that, we'll have to integrate the 1. So we get x e to the x to the 2024 minus integral x times now the derivative of the e to the x to the 2024. So that's 2024 x to the 2023 e to the x to the 2024. It's all just chain rule dx plus integral 2024 x to the 2024 and e to the x to the 2024 dx. So that's entire factor. Now notice that we have an x and x to the 2023, so that will combine to give us x to the 2024, and that is exactly the same term as this term. The only thing is there's a minus here, there's a plus here, so those will cancel off nicely, and we just have x times e to the x to the 2024 plus c, because it was an indefinite integral. Okay, moving on. And again, if you have any questions at any step, please feel free to comment. Integral ln of x plus 1 divided by x to the x plus x to the minus x. Now let's do one thing. We can get all positive powers in the denominator, and I forgot my dx, sorry for that. Let's get all positive powers in the denominator, so that means we can write this as x to the x times ln of x plus 1 divided by x to the x the whole squared plus 1 dx. You can divide by x to the x on the numerator and denominator and check that we indeed get this form back. It's just skipping those small trivial steps, because notice that if we take y to be x to the x, the natural log of y will be x times ln x. So we have 1 over y if we differentiate both sides. Dy dx is just product rule ln x plus x over x, which is just ln of x plus 1. So dy over dx in totality is just y times, y is x to the x, times that factor ln x plus 1, which is exactly what we have here in the numerator. So when we do that substitution, dy is just this factor, and that's nice because now we can integrate. So I will just be dy, that entire factor in the numerator, and we have y squared plus 1 because y was x to the x. So we just have y squared plus 1. And that is pretty simple to calculate. That is just inverse tan inverse of y plus c, and we know what y is. We have to resubstitute back. So tan inverse of x to the x plus c, and that's it. That's how we do it. That's the answer. Moving on to the next one. Question number, what is it? 4, I think. Yes. Question number 4. So we have sine squared plus cosine squared ds. Now notice what's happening here. It's not really a sine. Maybe I mispronounced it, but the fact is we have to treat I and n as constants, and same with the c and o. So notice the only variable that we're integrating is s here. So it's a linear in the first term and a quadratic in the second one. And maybe I should bracket that out. So how do we integrate a linear? We have s squared over 2, in squared because we're treating them as constants, plus cosine co s cubed over 3 because that's how we integrate those quadratics, plus c, and that's it. This was a very strange question, but that's the answer, believe it or not. Moving on. Question number 5. We have integral 1/4 to 4 arctan of x over x dx. Now the bounds of integration should be suggestive that we have to use this reciprocal substitution. U equals 1 over x. So du is minus 1 over x squared dx. When we do that, the bounds remain the same because we're absorbing the minus sign because of the denominator linear factor. So 1/4 to 4. We have inverse tan of 1 over x after all the cancellations, because we'll have a 1 over x squared from this dx factor, and we have a 1 over x from that x. Or maybe I should change it to u because I said I was going to use u. du. There you go. So when I add both of them up, 2I is integral 1/4 to 4. We can change the u back to an x because it's a definite integral. Inverse tan of x plus inverse tan 1 over x, all divided by x dx. Now I'm going to use a very powerful property. Notice that arctan of x plus arctan of 1 over x equal pi over 2 for x greater than 0. And x is indeed greater than 0. X is between 1/4 and 4. Both of them are positive. So this simplifies dramatically. Give us pi over 2, 1/4 to 4 dx over x, which is this natural log. So we have natural log of 4 minus natural log of 1 over 4. We can use the properties of natural log to give us pi over 2 times natural log of 4. The 2's cancel. We have pi times natural log of 4, but we have to divide by the 2 because we had 2i over there. So we have pi ln 2 because natural log of 4 is 2 squared, and we'll have 2 ln 2, and that 2 will cancel with that 2. So that's the end of that one. Let's do another one now. 6. Integral minus infinity to infinity. So the entire range, e to the minus x squared over e to the x plus 1 dx. Now, we can try using the negative symmetry. So x equals minus x will actually give us integral minus infinity to infinity, e to the minus u squared over e to the minus u plus 1 du. And if we again try to get a positive exponent in the denominator, we have e to the u, e to the minus u squared over e to the u plus 1 du. And when we add both integrals, the original one that we had on top and the one on the bottom, and again, using the same variable, let's say let's change x back to u because it's a definite integral, e to the u plus 1 over e to the u plus 1 e to the minus u squared du, and that will happily cancel off. So we just have the entire Gaussian integral, which we know, I've made a playlist on it, is square root pi. So the final answer, square root pi over 2. That's it. That's done. Now the next one, question number 7. Integral 0 to 1, third root of x times the floor function of the cube root of x dx. So when you see questions like that, a good strategy is to set the variable inside the floor function or the fractional part function to be y. So if I set y to be 1 over cube root of x, that's just x to the minus 1/3 power. So dy is just minus 1/3 x to the minus 4/3 dx, which if we simplify carefully is y to the 4th dx. So we can solve for dx in terms of dy. So dx is minus 3 y to the minus 4 dy. And just plug this all in the original integral that we have here. So integral now, if you notice the bounds are going from 1 to infinity, because when x goes to 0, y will go to infinity, and then when x goes to 1, y goes to 1. But then with the minus, we flip the bounds around. So integral 1 to infinity, 3 over y to the 5, floor of y dy. And now we can break this interval into discretize this interval. So sum from n equals 1 to infinity, integral n to n plus 1. The advantage of that is now the floor of y is just n, the lowest bound of the integral. So 3n over y to the phi dy, which is quite simple to evaluate. We get minus 3 over 4 outside. Sum from 1 to infinity, n over n plus 1 to the 4th minus n over n to the 4th. Now we need that minus because n plus 1 in the denominator is quite large. So we use the minus to switch it around so that, we ensure that we have a positive answer. So 3 over 4, sum n equals 1 to infinity, n over n to the 4th minus n plus 1 over n plus 1 to the 4th. And that, sorry, we have an n there, not n plus 1. Now we can just cancel or reindex, add and subtract a few terms to simplify this series. So just keep the first term as it is, then add plus 1 in the numerator of the second one. And since we have added that, we will have to bear the cost of subtracting the 1 with the minus. So that's 1 over n plus 1 to the 4th. Now if we just evaluate these first two terms, they're a telescoping series. So the only term that remains is 1, because the term at infinity, and we also always need to care about the term at infinity for the asymptotic behavior, that term will go to 0, having a power in the denominator that's greater than the numerator. So we will just have 3 over 4 sum n equals 1. Sorry, we have the 1 outside, 1 plus sum n equals 1 to infinity. 1 over n plus 1, whole thing to the 4th power. It would be a mistake to write the 1 inside the sum because that means we're summing the 1 infinite times, and that's, well, divergent for these purposes. We can reindex all of this because if you notice the second term, if we take n equals 1, we have 1 over 2 to the 4th. So with the 1, we can just write this sum n equals 1 to infinity, 1 over n to the 4th. And that is just the Riemann zeta of 4, which has a nice value of pi to the 4th by 90, which you can also calculate using Fourier series of x squared and use the Parseval's theorem on both sides. We end up with, of course, but that is the, I believe, the answer. Now, moving on, number 8. Integral 0 to infinity dx over x plus 1 ln squared of x plus 1. Okay. Now, one thing we can actually try is using, again, the reciprocal substitution. So with that, the dx is minus 1 over u squared du. So I just becomes, with everything, the integral bounds can be the same, du over u plus 1. And the ln squared will be the same because it's being squared. Ln of 1 over u is minus ln u, but we are squaring the entire thing. Yeah, there you go. And now we can partial fraction decomposition. So the term apart from the natural log squared, the product of u and u plus 1 in the denominator, we can write as a partial fraction. So that's 1 over u minus 1 over u plus 1. 1 over ln squared of u plus 1 du. Take the first term out, which is just du over u times, should bracket ln squared u plus 1. And notice that the second term is just I. It's just, we started with an x. Here. We just got shifted to a u, and that's fine because it's a definite integral. So that's I, and that's nice. We can add that. So we have 2I integral 0 to infinity du over u times ln squared u plus 1. Now, we use a nice substitution, y equals ln u, because we notice with a 1 over u factor there. Since dy is 1 over u du, so 2I is just integral minus infinity to infinity, correctly changing the bounds, dy over y squared plus 1, which is just tan inverse y from minus infinity to infinity, which is just pi. So I is simply pi over 2. That's the answer. Now the penultimate question, let's move on. We're marching forward. And that's why I said, if you have questions, let me know. Integral 0 to 2 pi 1 over 1 plus square root 1 minus sine squared x dx. Now, this is kind of an important question, although it might seem kind of basic. It's because we have 1 square root 1 minus sine squared x. You might say, well, 1 minus sine squared is cosine squared, and take the square root of that, you'll get a cosine, but not really. You need an absolute value of the cosine. Because if cosine is negative in the denominator, we'll have a minus 1 at its highest value, giving us a 0 in the denominator that blows up. So we really need the absolute value for convergence. And when we do that, we can just write this, because it's an absolute value of the cosine, 4 times the value from 0 to pi over 2 because of the periodicity of the cosine. Dx over 1 plus cosine x. And now we just use the double angle formula for the cosine. We end up with 2 cosine squared x by 2, which, one of the 2's will cancel. 2 0 to pi over 2 secant squared x by 2 dx, which again, using the reverse chain rule, we get 4 times tan of x by 2, because secant squared is the derivative of the tan, from 0 to pi over 2. So we have tan of pi over 2 over 2, which is pi over 4. Tan of pi over 4 is 1, and minus tan of 0, which is 0. So we just end up with 4 times 1, which is 4. And moving on to the last one, finally, we have integral from 0 to infinity e to the minus t squared cosine of 2xt dt. And to solve this, actually, we can just complexify the cosine and say we're taking the real part, 0 to infinity of e to the minus t squared e to the I 2xt, because the real part of e to the ix is just cosine x. When I do that, it's nice. We can complete the square, e to the minus t minus ix whole squared e to the minus x squared dt. You can check the algebra, the completing of the square. You get e to the minus x squared real part of 0 to infinity. Now we can do one substitution. We can set t minus ix goes to t, and this is fine because in the complex plane there's no poles. So when we rotate our axis, when we're taking this contour, there's no pole in between. So this choice is justified. There's no pole in between. So we can, this contour, this integral along this contour, this line is equal to the integral along the vertical line, and that's fine. So with that justification, we have e to the minus t squared dt, which is half the Gaussian integral. So we have e to the minus x squared over 2 times square root pi. And that's perfect. That's brilliant. We've solved the problem. There's many ways of doing it. We could have also taken Feynman integration with respect to the x and then gotten some sort of like a differential equation. But again, this is a very nice way of solving. This saves time. So see you in the next video. Hopefully I will cover the other problems, which is question 10 or 11 to 20, and then 21 to 30 in a separate video. So please like, share, and subscribe to my channel, guys, and peace out. Keep doing math. See you next time.